Good morning. So, we are discussing about the pattern recognition problem, and we are talking about the different discriminant functions which are helpful for classification of unknown patterns. So, earlier what we have seen is, starting from the Bayes decision theory, that if you know the probability density function, or the parametric form of the probability density function, we can design the different discriminant functions for pattern classification or classification of pattern vectors or feature vectors. We have discussed about specific case that if the probability density function is either Gaussian or normal distribution function, and we know the mean and the covariance matrices of the different classes, then we can have different types of discriminant functions or different types of decision boundaries among different classes. In particular, if the covariance matrix of all the classes are same, of the samples belonging to all the classes are same, then we have seen that the discriminant function that you get is a linear discriminant function. Whereas, if different classes or the samples belonging to different classes, they have different covariance matrices, arbitrary covariant matrices, in that case, in general, the kind of discriminant function that we get is a quadratic discriminant function. So, in multi-dimension, it is called hyperquadrics, and accordingly, the decision surface between two different classes in one case is hyperplane, and if the covariance matrices are arbitrary or different classes have different covariance matrices, then the decision surface between two classes becomes a hyperquadric surface. However, following the Bayes decision theory, if we want to have the discriminant function, we have to know that what is the parametric form of the probability density function of the samples belonging to that particular class. And given the number of samples, if we know the parametric form of the probability density function, we may not know the parameter values exactly. If we know the parametric form of the probability density function, then we have seen in previous classes that we can have the maximum likelihood estimate of those parameter values. So, this maximum likelihood estimate says that these are the best representations or best supported by the samples which are available from that particular class. Okay. And then also we have discussed about the dimensionality problem, because not every feature has equal discriminating power. So, following the principal component analysis or following the multiple discriminant analysis, we can reduce the dimensionality of the feature vectors, ensuring that the features in the reduced dimensional feature vector will have better discriminating power than the features which are avoided. Okay. So, now today we will discuss about this same linear discriminant function, but unlike in case of what we have obtained from Bayes decision theory, that we have to know the parametric form of the probability density function. In case the parametric form of the probability density function is not known. So, then what we have to do is, we have to design the discriminant function, or we have to find out the decision boundary between two different classes by using the samples which are available from different classes. So, here we do not assume any probability density function. So, we know, so initially we will discuss about the linearly separable classes. So, we know that the classes are linearly separable, and because we are discussing about the supervised learning process. So, we know a set of samples belonging to one class omega 1, we know set of samples belonging to another class omega 2. So, using this information and without using any assumption of the nature of the probability density function, we have to find out the linear discriminant function, which discriminates between these two different classes. Okay. So, we will assume that the classes are linearly separable, and as the classes are linearly separable, so we should be able to formulate, we should be able to design a linear discriminant function, okay, where no probability density function form is assumed. Okay. So, because the discriminant function will be linear, so we know that a linear equation can always be written as g x is equal to w transpose x plus w naught, okay, where x is the feature vector and we assume that the feature vector x is of dimension d. So, it is d dimensional feature vector. Okay. W is called the weight vector, okay, and W naught is called the bias or threshold weight. Okay. So, you see that this particular expression is a linear expression, where x is a d dimensional vector, W is also a d dimensional vector, and this term W transpose x is nothing but inner product of vector W with a vector x, right. And our decision criteria will be that for an unknown feature vector x, if g x is greater than 0, then we classify x to belong to class omega 1. If it is less than 0, then x will be classified to class omega 2, and if it is equal to 0, then we say x is on the decision boundary. Okay. So, if g x is greater than 0, we decide x belongs to class omega 1. If it is less than 0, we decide x belongs to class omega 2. If g x is equal to 0, then x is on the decision boundary. So, the decision boundary between two classes x 1 omega 1 and omega 2 is given by the equation g x is equal to 0 or W transpose x plus W naught, that is equal to 0. Now, let us see that what is the nature of this weight vector W. Okay. So, to find out the nature of the weight vector W, let us take 2 points on the decision boundary. So, what we are interested in is the nature of weight vector W. So, we take 2 points x 1 and x 2 on decision boundary. Okay. Now, because x 1 and x 2 are on the decision boundary, so W transpose x 1 plus W naught will be equal to W transpose x 2 plus W naught, and both of them equal to 0, because x 1 and x 2 are lying on the decision boundary. So, we can simply write that W transpose x 1 plus W naught is equal to W transpose x 2 plus W naught. Okay. So, from this you find that W transpose x 1 minus x 2, this is equal to 0. Now, what is this x 1 minus x 2? X 1 minus x 2 is nothing but a vector lying on the decision surface, because x 1 is on the decision surface, that is a vector. X 2 is also a vector lying on the decision surface. X 1 minus x 2 is a vector which is lying on the decision surface, and W transpose x 1 minus x 2 is the inner product of W with the vector x 1 minus x 2. And because this inner product is equal to 0, so that clearly indicates that this vector W is orthogonal to any vector lying on the decision surface, because we have taken x 1 and x 2 arbitrarily. So, W transpose x 1 minus x 2 equal to 0, that indicates that vector W is orthogonal to any vector lying on the decision surface. Okay. That means, the vector W is orthogonal to the decision surface. Okay. And this surface being a planar surface or a linear surface in d dimensional space, we call it an hyperplane. Okay. And let us represent that hyperplane by H is the hyperplane. Okay. So, this vector W is orthogonal to hyperplane H. Now, what does this G x actually represent? G x, what does it represent? You will find that G x gives you some measure of the algebraic distance of vector x from the decision surface or from the hyperplane H. Okay. So, this G x, this gives an algebraic measure of x from H. Okay. Let us see how. How do we say that this G x represents an algebraic measure? It is not the exact distance value, but it is a measure of the distance value. I mean something proportional to the distance, algebraic distance of the vector x from the decision surface from the hyperplane H. How does it give us that measure? Let us consider a case in 3 dimension. So, I have a 3 dimensional space with the vector components represented by x 1, x 2 and x 3. Okay. Suppose I have a decision surface, so something like this. In this 3 dimensional plane. So, this is my plane H. Okay. And let me take a point x somewhere over here. Okay. And when I take this point x over here, let me drop a perpendicular from this point x onto the hyperplane. And let me assume that x p represents the foot of the perpendicular on this hyperplane. Okay. And suppose the distance between x p and x, the length of this vector joining x p and x is given by say r. Okay. Now, if it is so, in that case I can write x is equal to x p okay, plus r is the distance okay, multiplied by w upon mod of w, because we have seen earlier that the vector w is orthogonal to the hyperplane H, orthogonal to the decision surface. So, the direction of w is in the same direction of x p to x, because x p to x, this vector is orthogonal to this hyperplane, w is also orthogonal to the hyperplane. So, this is w. So, I can write this x is equal to x p plus r into w upon mod of w, because w upon mod of w is the unit vector in the direction perpendicular to the hyperplane. Okay. So, I can write it in this form, and when I write it like this, then what is g x? G x is nothing but w transpose x plus w naught, okay, which in this case will be w transpose x p plus w naught plus r into w transpose w upon mod of w. Is it okay? I am simply replacing this x by this x p plus r into w upon mod of w. Now, out of this, the point x p, which is foot of the perpendicular from x onto the hyperplane, that lies on the decision surface. Okay. So, w transpose x p plus w naught, because x p is on the hypersurface, w transpose x p plus w naught will be equal to 0, okay, because it is on the decision surface. So, what I get is this will be simply r into, and what is w transpose w? This is nothing but mod of w square. Okay. So, what I simply get is r into mod of w. Okay. So, you find that this discriminant function g x, the value that you get, is nothing but r, we said, is the distance, perpendicular distance or orthogonal distance of point x from the decision surface, because it is the distance between x p and x. Okay. So, this r is the orthogonal distance of point x from the decision surface. So, this g x is the orthogonal distance scaled up by the modulus of w. Okay. And if I want to find out what is the actual orthogonal distance, that is given by r is equal to g x upon mod of w. Okay. So, that is why we said that this discriminant function g x actually gives you a measure, algebraic measure of the distance of the point, orthogonal distance of vector x from the decision surface. Okay. Now, why is it, or why are we calling it algebraic distance?
Sir, here only the first term will be, product term will be only 0.
Which
How
one?
can w transpose x p plus w naught came 0?
You come to our original expression, g x is equal to w transpose x plus w naught.
Yes, sir.
Okay. This is your discriminant function. What we said is, if g x is greater than 0, then x belongs to omega naught, omega 1, less than 0, x belongs to omega 2. If it is equal to 0, then x is on the decision boundary. Okay. That is g x is equal to 0, not w transpose x equal to 0, and g x is w transpose x plus w naught. Okay. So, because x p is lying on the decision surface, so g of x p will be equal to 0, and g of x p is nothing but w transpose x p plus w naught. Is that okay? Right. So, here why we are calling it as algebraic distance is that if r is positive, then x lies on the positive side of the hyperplane. If r is negative, then x is on the negative side of the hyperplane. Okay. And this expression that I have said, that r is equal to g x upon mod of w. Okay. This is an expression which is nothing new. I mean, this is what you have already done in your school level mathematics, because we know that in school level mathematics what you have done is, if I have the equation of a straight line given say a x plus b y plus c is equal to 0, come to your coordinate geometry, okay, and given a point x 1 y 1, what is the distance of point x 1 y 1 from this straight line, which is nothing but a x 1 plus b y 1 plus c upon square root of a square plus, okay. And if you compare this expression with this expression, they are exactly identical. This expression is in the 2 dimension, this expression is in d dimension, or the dimensionality has increased. Okay. So, what we have derived over here is nothing new, there is something that you already have done in your school level mathematics, right. So, what we are saying here is that if r is positive, then the vector x lies on the positive side of the hyperplane. If r is negative, then x lies on the negative side of the hyperplane. Okay. And what is the distance of origin from the hyperplane? Okay. So, distance of origin from the hyperplane, that is simply given by W naught upon mod of W. Okay. So, here if W naught is positive, then origin lies on the positive side of the hyperplane. If W naught is negative, then origin lies on the negative side of the hyperplane. Okay. And if W naught is equal to 0, then the hyperplane passes through the origin. Okay. So, if W naught is equal to 0, then the hyperplane passes through the origin, and not only that, your discriminant function takes a particular form, that g x will be simply given by W transpose x, okay, where I do not have any bias of threshold weight, and this is a form which is called homogeneous form. And in mathematics, it is always convenient that if I can represent an expression in a homogeneous form, okay, that avoids many of the problems that we may face while we try to analyze different given problems. Okay. So, after we discuss about the nature of the decision surface, if it is a hyperplane, then what are the conditions or what are the different positions of the hyperplane, okay, that we can have. Then the hyperplane has two sides. Actually, hyperplane divides your feature space, d dimensional space, into two half spaces. Okay. One of the half space is positive, the other half space is negative. If a sample, if a feature vector falls on the positive half space, then it will be classified into one class. If the feature vector falls on the negative half surface, it will be classified into another class. If it is on the decision surface, then we cannot classify it actually, because it is equally likely that it may belong to class omega 1 or it may belong to class omega 1 omega 2. So, if the sample falls on the decision surface or falls on the hyperplane, we cannot really take any decision, it is an ambiguous case. Okay. Now, after discussing this, let us see that how we can design this vector W. Okay. Ultimately, because it is a linear classifier, I have to find out the discriminant function g x, and if I can find out the feature vector W and the threshold weight, so not feature vector, the weight vector W, and the bias of the threshold weight W naught, then my linear classifier is designed. Okay. So, I have to design or I have to decide about W and W naught based on the samples that are available, because it is supervised learning. So, we are given samples from both the classes omega 1 and omega 2. So, I have to decide W and W naught based on the information available from those known labeled samples. Okay. So, let us talk about design of the weight vector W. Okay. And here again, for simplicity, initially we will assume that we have two category linearly separable case. Later on, we will generalize this to multiple category problem, where we have C number of classes. But to start with, let us start with only two category case, that is we have classes omega 1 and omega 2. Okay. So, what we have so far is we know that we have to have a discriminant function of the form g x is equal to W transpose x plus W naught. Okay. And as we said that this expression of the discriminant function, this is not in the homogeneous form. However, if I can convert it into homogeneous form, then my analysis will be easier or my design will be easier. Okay. So, how we can convert this into an homogeneous form? I can very easily convert this into homogeneous form if I write this expression in the form A transpose y, okay, where A is my modified weight vector, and this modified weight vector will include all the components of the weight vector W and also the bias weight or the threshold weight W naught. Okay. So, if this weight vector A has to include all the components of W as well as W naught, then I have to do some augmentation in the feature vector x. Okay. So, what I will do is I will write, so this y is actually augmented feature vector x. Okay. So, what will be y? Y will be nothing but I have to take all the components of x. So, I have to take the first component x 1, second component x 2, all the d components of x, that is up to x d, and I make last component is equal to 1. Okay. So, if I do that for every x, if I augment 1 to give me an augmented feature vector y, then I can write this expression in an homogeneous form as A transpose y. Simply because what is this A transpose y? A transpose y is nothing but W 1, W 2 up to W d, W naught. This is a row vector because I have to take transpose multiplied by the column vector x 1, x 2 up to x d, then 1. Okay. So, if you do this multiplication, this multiplication is nothing but summation of W I x I varying from 1 to d plus So, up to d components are taken care by this summation term x 1 w 1 plus x 2 w 2 plus x 3 w 3 up to plus x d w d. So, this is x I w I times x I varying from 1 to d plus w naught into 1. So, plus w naught, right, which is nothing but w transpose x plus w naught. Okay. So, I get exactly the same expression as this. Only thing I have to do is I have to augment 1 to the feature vector x, giving me an augmented feature vector y. Okay. And after having this homogeneous expression, my decision rule remains the same, that if A transpose y I for the ith augmented feature vector x I, okay, is greater than 0, then I decide that y I or the corresponding original vector x I that belongs to class omega 1. Okay. And if it is less than 0, then I decide that y I or the corresponding feature vector x I. Okay. Do not confuse between this subscript and this subscript. Here I have meant this subscript means the ith component of the feature vector, and this means ith feature vector. Okay. So, if it is less than 0, then my decision will be that this belongs to class omega 2. Is that okay? So, my decision rule remains the same, only thing is I have a modified formulation of the same problem. Now, let us see that how we can really design this weight vector w, or in this case the weight vector A, because A consists of all the components of w and also the bias vector or the threshold vector w naught. Okay. So, our aim is to design the weight vector A by using the knowledge of the leveled samples from class omega 1 as well as class omega 2. Okay. So, we assume that we have n number of samples, and when I say n number of samples, that means we have n number of augmented samples, where I have augmented 1, I appended 1 to each of the feature vector. Okay. So, I have n number of samples called training samples, because these are the samples which are used to train the classifier. Okay. So, this n number of samples omega y 1, y 2 up to y n. So, each of these y i's are actually augmented feature vectors by appending 1 to the original vector x. Okay. Some of these samples, some of these feature vectors are labeled as class omega 1, some of these feature vectors are labeled as class omega 2. Okay. Now, for a particular feature vector, augmented feature vector y I, as I said earlier, my decision rule will be A transpose y I greater than 0 indicates y I is in class omega 1, less than 0 indicates y I is in class omega 2. Okay. If it is equal to 0, I can't take any decision, right. So, if I now what I have to do is I have to find out the value of this weight vector w. I have some samples which are labeled as class omega 1, I have some samples which are labeled to belong to class omega 2. Okay. Now, given a weight vector A, if I take all the samples which are labeled as omega 1, if I find that for each of those samples A transpose y I is greater than 0. Okay. That means that given weight vector A is correctly classifying all the samples, all the feature vectors which are labeled as class omega 1. If I also find that for the same weight vector A, all the samples belonging to class omega 2 which are labeled as belonging to class omega 2, for all of them A transpose y I is less than 0, then the feature vector, then the weight vector A is also classifying the samples which are labeled as belonging to class omega 2. Okay. So, that particular A which we have obtained, that is the correct weight vector, because it is classifying correctly all the samples which are in class omega 1. It is also classifying correctly all the samples which are labeled as omega 2. So, that is a feature vector that we want, but how to obtain such a feature vector? Okay. So, to obtain such a feature vector, another modification that can be done is that now you see that I have two decision criteria. In one case, I am checking that it has to be A transpose y I has to be greater than 0. In another case, I am checking that A transpose y I has to be less than 0. So, instead of having these two different criteria, can't we have a single criteria, that if some condition is true, a single condition is true, I say that the sample is classified correctly. If the condition is not true, single condition, if that is not true, I decide that the sample is not classified correctly. Okay. So, can't I make something like this, that if A transpose y I is greater than 0, I will say sample is correctly classified, irrespective of whether this feature vector y I is labeled as belonging to class omega 1 or it is labeled as belonging to class omega 2. Okay. So, I do not look at the level of the feature vector y, whatever be its level. If I can somehow convert this decision in the form that A transpose y I irrespective of level of y I, if A transpose y I is greater than 0, I will say that y I is correctly classified. Otherwise, I will say that it is misclassified. So, otherwise includes less than 0 as well as equal to 0, because equal to 0 does not give me any information. I cannot decide about the class belongingness of the sample. Okay. So, whether it is less than 0 or equal to 0, I will say it is misclassified. If it is greater than 0, I will say it is correctly classified. So, how we can do that? From here you see that if A transpose y I is greater than 0, then y I belongs to class omega 1. If A transpose y I is less than 0, then y I belongs to class omega 2. Okay. So, why do not I do one thing? I take all the samples which are labeled as omega 2, okay, and then negate it. So, instead of considering y I consider minus y I, okay, because I know all the training samples which are given from class omega 2. Okay. So, I simply negate all those training samples. So, when I try to find out this feature vector, this weight vector A, the samples belonging to class omega 1, I will take them as it is. As it is means after augmentation, after appending 1. And for the samples belonging to class omega 2, I will augment them by appending 1 and then take negative of it. Okay. So, if I take the negative, then this A transpose y I, which is supposed to be less than 0, now it will be greater than 0. So, I get an uniform decision criteria after negating all the samples belonging to class omega 2, that in all the cases I should have A transpose y I greater than 0. Okay. So, I will say that if A transpose y I is greater than 0, my sample is correctly classified irrespective of whether the sample is taken from class omega 1 or the sample is taken from class omega 2. Is that okay? So, what I will do is I will take all the samples from class omega 1 as it is, the samples from class omega 2 I will take negate of it, okay, and then use this for designing the classifier or to find out what will be the weight vector A. Okay. Then again, it is better that if we can define some sort of criteria function. Okay. So, we take some sort of criteria function say J A and the J A has to be minimized if A is the correct weight vector. Okay. That means, for that weight vector A which classifies all the training samples correctly, J A will be minimum. Okay. So, I will define some sort of criteria function, we will see what kind of criteria function we can have, and then my job will be by varying A in an iterative way, I have to minimize this J A, and this J A has to take a minimum value when I reach an weight vector A which properly classifies all the training samples. Okay. And for minimization of this J A, the criteria function J A, we can make use of an approach which is called gradient descent approach or gradient descent procedure. What is the gradient descent procedure? Suppose at the kth iteration, I know what is A k. Okay. A k is the value of vector A, weight vector A in the kth iteration. Okay. Then I have to update this weight vector A. So, from kth iteration, I have to go to k plus first iteration. Okay. So, from here, when I want to find out the value of A in the k plus first iteration, that is A k plus 1, which will be equal to A k minus sum eta k times grad of J A k. This is what is gradient descent procedure. Okay. And what is this eta k? Eta k actually specifies the learning rate. So, what does this procedure mean? Suppose I have a criteria function, so something like this. Okay. This is the point where it is minimum. Suppose in the kth instant, whatever value of A k I have, the criteria function is somewhere over here. So, I put that this criteria function, this is J A with respect to A. Okay. So, at the kth iteration, suppose this is my A k and the criteria function, value of the criteria function is this is J A k, right. If I take the gradient of this, gradient will increase in this particular direction. Okay. So, what I am doing is, I am moving A k in a direction which is negative to the gradient, right. That means, I am moving A k in this particular direction. So, in k plus first iteration, depending upon the value of this eta k which is learning rate, I may move either over here or over here or over here or even somewhere over here. So, if the value of eta k, which is called learning rate, if the eta k is very large, then when I modify this a k plus 1 may be found somewhere over here. That means, I am overshooting the minimum value. Where if eta k is very small, I may land somewhere over here. So, which says that your learning rate is very slow. If eta k is very large, I may overshoot the solution and this may lead to oscillation. So, what I will have is from over here I will move to this point, then to this point, then to this point, then to this point and so on. So, I will have oscillation around the solution vector. Is that okay? So, this is what this gradient descent procedure does, that you start with an initial arbitrary value of the weight vector. For that weight vector, you find out what is the value of the criteria function, then try to minimize the criteria function following the gradient descent procedure. Okay. Or this is also called the procedure of steepest descent. That means, you follow the negative of the maximum gradient value, path of the negative of the maximum gradient value. So, this is also called steepest descent procedure. Is that okay? Now, one such criteria function, as I said, that we will talk about the perceptron criteria function. One such criteria function is called perceptron criteria. Okay. Now, what is this perceptron criteria? Let us assume that at the kth instant, somehow we have been able to obtain the weight vector a k. I am not saying how we have obtained it. Somehow in the kth iteration, I have been able to find out the weight vector a k, because it is in the kth iteration, I say it is a k. Okay. Now, this a k, I will try whether it can correctly classify all the training vectors or not, all the training samples or not. And when I consider all these training samples, as I said that the training sample from class omega 2, they will be negated, after augmentation they will be negated. Training samples belonging to class omega 1, they will simply be augmented, they will not be negated. So, that if all the samples are correctly classified, for all the samples I must have a k transpose y greater than 0. If there is any sample for which a k transpose y is not greater than 0, it may be less than 0, it may be equal to 0. I say that that particular training sample is not correctly classified. Okay. So, our aim will be to find out an weight vector A which will classify all the training samples correctly. I do not want to have even a single training sample which is not correctly classified or which is misclassified, right. So, I can try to design a criteria function which will make use of the training samples which are not correctly classified. Okay. Because if the training sample is correctly classified, I do not bother about it, because my job is done. If the sample is not correctly classified, then I have to think to modify my weight vector. So, the criteria function that I want to design, I will make use of the training samples which are not correctly classified by that particular weight vector a k. So, accordingly, I can define the criteria function, I call it JPA, because we are saying it perceptron criteria, right, which is equal to sum of minus A transpose y for all y which are misclassified. Is that okay? So, find that if y is misclassified, then A transpose y, it is negative. Okay. So, minus A transpose y has to be positive, right. So, as a result, this perceptron criteria function JPA, it can never have a negative value. It will always have a positive value. The minimum value can be 0. Okay. So, I have a global minimum for this criteria, perceptron criteria function, and this global minimum I can find out by gradient descent procedure. Is that okay? So, if I want to apply that gradient descent procedure, then I have to take the gradient of JPA with respect to this weight vector A. Is that okay? So, I will have grad of JPA with respect to A, which is nothing but sum of, if I take the gradient of A transpose y with respect to A, it simply becomes y, right. So, it is simply sum of minus y for all y misclassified. Is that okay? And my update rule or the algorithm to find out this weight vector A will simply be, I take an initial weight vector A 0 arbitrarily. Okay. So, A 0 will be arbitrary. Then A k plus 1, that is the weight vector in the k plus first iteration, will be simply A k plus eta k, which is the learning rate, into summation of y for all y misclassified. Okay. So, this is the algorithm for design of my weight vector. So, once I have chosen A 1, A 0 arbitrarily, from A 0 I can find out what is A 2 by following this updation rule. A 2 is nothing but A 1, from A 0 I can find out A 1, which is nothing but A 0 plus eta k, which is the learning rate, into summation of all the y, all the vectors y, which are actually misclassified by A 0. Okay. So, I have A 1, from A 1 I can find out A 2, A 2 is nothing but A 1 plus again eta k plus summation of all those samples which are misclassified by A 1. Okay. So, by doing this iteratively, I can finally find out an weight vector if which will finally classify properly all the training samples. Maybe the number of iterations will be more depending upon your initial choice and the number of feature vectors that you have, the distribution of feature vectors. But if the feature vectors are linearly separable, I will get an weight vector which will properly classify all the training samples. Okay. So, we will stop here today. Next day we will continue with this